Hello, everyone. I'm Tanya Sridhar. I'm a postdoctoral researcher at U Delft, and today I'll present BISCAY, a practical radio KPI driven congestion control algorithm for mobile networks. This is a joint work with my colleagues from University of Edinburgh. Mobile phones now generate a significant percentage of all internet traffic. About 43% of the global internet traffic comes from mobile users, and 70% of the world's population uses a smartphone. 5G penetration is also increasing rapidly. By 2030, we expect close to 5.5 billion subscribers, with 50% of mobile connections on 5G networks. This growth is being driven by next generation applications that demand both low latency and high bandwidth. Cloud gaming, AR, VR, video conferencing, and live HD streaming all require a robust congestion control. And cellular networks make this a challenging problem. The congestion control is designed for end to end operations between a cellular device and an internet supported service. This means that congestion control needs to track what's happening at the air interface to utilize the available bandwidth to the fullest. However, the available cellular bandwidth fluctuates rapidly and unpredictably. These fluctuations may be from user mobility, wireless channel dynamics, interference, handovers, and varying distance to the base station. The plot here highlights these challenges. It is from a trace from a commodity 5G phone while moving. Notice how the bandwidth swings from 10 to 30 Mbps within seconds. The end to end view, that is, what the traditional congestion control algorithms observe, is shown in green, and the actual 5G link capacity is shown in blue. This highlights that more often than not, the wireless link is the bottleneck. But before we go further, let me briefly explain congestion control. Congestion control manages the rate at which data is sent so that we don't overwhelm the network. There is a sender, a bottleneck link somewhere in the path, and a receiver. The graph here shows the data delivery rate and the round trip time as functions of data in flight. Now, as we increase the data in flight, we move through three regimes. First, the app limited region, where we are not sending enough to fill the pipe. Then we reach the bottleneck limited region. Now, if we push any further, we enter the buffer limited region, where access data queues up, increasing delay but not really improving the throughput. So the sweet spot is right at the highlighted boundary, and it is known as the Klein-Rock's operating point. It is actually the bandwidth delay product, or the BDP, where we futilely utilize the bottleneck capacity with a minimum queuing delay. The goal of any congestion control algorithm is to find this operating point so as to keep the file just full but not fuller. And here's the challenge. In cellular networks, the bandwidth fluctuates rapidly. The optimal operating point now keeps moving. Traditional congestion control algorithms that rely on end to end signals like loss or delay react too slowly to track these rapid changes. In this work, we try to solve this problem by using real time radio KPIs. So, the first challenge now is extracting the radio KPIs in real time. Standard methods like Android telephony API give some KPIs, but with limited coverage and coarse granularity, typically 1 or 2 seconds between the updates. That is too slow for congestion control. Advanced methods use the diagnostic interface. Tools like QXTM can access detailed KPIs, but they require the phone to be connected to a computer. This is not practical for our deployed systems. Mobile Insight is one possible option. It is an open source alternative that can access the chipset KPIs on the device. It's in fact used in several research projects. But here's the problem. Mobile Insight doesn't account for modem's internal buffering. The Qualcomm chipset batches these diagnostic messages in a ring buffer and releases them roughly once per second. Even though these individual messages have fine grained timestamps, they arrive in batches, so the effective granularity is about 1 second. For congestion control, where the decisions happen at RTT timescales, 1 second granularity is quite inadequate. Therefore, we can't use the existing solutions. There are also a few other challenges beyond KPI extraction, such as existing works don't agree on which KPIs are relevant for bandwidth estimation. Different papers use disjoint set of KPIs, and there are contradictory claims about which ones are actually better. Additionally, the models used to map KPI to bandwidths are unreliable. So linear models aren't accurate enough, and machine learning models tend to overfit to specific conditions and don't really generalize well. Finally, there is also this deployability problem. Most prior work stops after estimating bandwidth. They don't provide a complete solution that can actually run on a real smartphone without root access or external hardware. So this brings us to our solution, BISCAY. BISCAY is a complete congestion control algorithm that addresses all these challenges. It can get radio KPIs in real time with fine granularity. It can accurately determine the radio link bandwidth from those extracted KPIs using 3GPP standard procedures. It also provides a complete congestion control solution, not just a bandwidth estimation. And finally, it can be deployed on a real phone without requiring root access or external hardware. So, at the heart of BISCAY is OpenDiag, our real time KPI extraction tool. OpenDiag has a novel in kernel design. That is, everything runs inside the Linux kernel, avoiding the overhead of crossing the user kernel boundary. It has a tightly coupled architecture that interfaces directly with the Qualcomm Diag module. OpenDiag has an efficient KPI focused processing framework. Instead of parsing entire packets like Mobile Insight, OpenDiag parses only the specific fields needed. The key innovation is our control channel. We reverse engineer how to instruct Qualcomm chipset to drain the internal ring buffer on demand. OpenDiag flushes this buffer every millisecond, eliminating the batching problem. Finally, we provide POSIX-like API through libod for applications that need KPI access. Now we wanted to evaluate the performance of OpenDiag. The figure on the top compares the KPI extraction granularity across different tools. We measured time between consecutive RSRP samples, which is a standard KPI in the most frequent diagnostic message. Commercial tools like Nemo Handy, Collie POC achieve roughly around 1 second granularity. The Android telephony API is also similar. Mobile Insight, despite accessing the Diag interface, also delivers approximately 1 second granularity. OpenDiag achieves approximately 11 milliseconds, and that's a 100 times improvement. In the bottom plot, we see the mobile, see with Mobile Insight, we get this staircase sort of a pattern. That is because modem batches messages internally and only releases them roughly every second. This granularity difference is fundamental. At 1 second sampling, you cannot capture the rapid bandwidth fluctuations that is characteristic of mobile networks. We also compared OpenDiag with Mobile Insight on message processing time as a function of the subscribed packets shown on the left. We found that OpenDiag remains in tens of microseconds regardless of the packet count. This is 3 orders of magnitudes over improvement over Mobile Insight, and it enables true real-time operation. On the right, we show battery consumption, which can be a concern for an always-on KPI extraction tool. The baseline here is screen on with minimum activity. We compared OpenDiag and Mobile Insight, both recording the KPIs needed for BISCAY. OpenDiag's battery degradation compared to baseline is negligible, which is not the case for Mobile Insight. So this validates OpenDiag is practical for continuous operation. So now the next question is, how do we convert the extracted KPIs to bandwidth? So for bandwidth determination, we look directly at 3GPP specifications. The modem already computes the bandwidth internally. From 3GPP, we identified the relevant KPIs and the formulas to compute available bandwidth. We implemented two methods. So method one follows the 3GPP transport block size calculation. That is, it uses the granted PRBs, TBS index, and the number of MIMO layers. Using these predefined 3GPP lookup tables, we compute bandwidth. For carrier aggregation, we sum across all these component carriers. The method two is a bit simpler. The MAC layer computes and reports the granted bytes as a diagnostic summary. This aggregates all carriers and MIMO streams across 4G and 5G at 100 millisecond granularity. We evaluate both these methodologies to validate our bandwidth determination approach. The heat map here shows Pearson correlation between different bandwidth estimates and ground throughput measured at the receiver. Our two methods, the 3GPP formula and the granted bytes, both achieve correlation above 0.95. Using raw KPIs directly, MCS or TBS or PRBs individually achieves only around 0.75 correlation. This is the reason why prior approaches that correlate raw KPIs to bandwidth are fundamentally limited. The time series plot also shows how closely our estimates track the actual bandwidth. The 3GPP calculation and the granted bytes overlay almost perfectly with the ground truth. So now we will focus on how BISCAY integrates OpenDiag and bandwidth information into congestion control. BISCAY is built on top of BBR. We chose BBR because it also uses bandwidth internally to calculate congestion window, making it an natural integration. However, we added several optimizations over BBR. We added multi-flow tracking for fairness. Secondly, there is a direct bandwidth input, while BBR must probe to find the estimate bandwidth using probe bandwidth and probe RTD phases. BISCAY directly injects the KPI measured bandwidth. This eliminates the probing overhead and provides more accurate timely estimates. Third is the bottleneck detection and fallback. BISCAY continuously compares the cellular bandwidth estimate with BBR's end-to-end estimate. If the wired segment becomes the bottleneck, BISCAY switches to standard BBR. Well, this is rare in practice, but it just ensures correct behavior. The result is a CCA that keeps the congestion window precisely matched to the available cellular capacity. We evaluate BISCAY extensively, but in the interest of time, in this presentation, we only show BISCAY performance with other congestion controls across four scenarios: mobile and static, on-peak and off-peak. We use Pantheon emulator with 260 traces from our measurement campaign for controlled comparison against 9 congestion control algorithms. The throughput is on y-axis, where higher indicates better. Delay is on x-axis but reverse, so the lower DLA appears on the right. So the top right corner represents the optimal performance, that is high throughput and low delay. Cubic, the Linux default shown in red, achieves high throughput but with extremely high delays. Wireless aware congestion control protocols like Sprout and Varus show improved delay in some scenarios, but this is inconsistent overall. Learning-based congestion control algorithms like PCC and Vavase show high variance, suggesting a bit overfitting. BISCAY consistently achieves the best throughput delay trade-off across all scenarios. We match or exceed throughput of aggressive congestion control algorithms while maintaining delays close to minimum. We also conducted real-world tests and deployed BISCAY on Google Pixel 5 and tested on a private 5G network and also public networks from Verizon and T-Mobile. Results confirm our emulation finding. BISCAY achieves 4.6% higher throughput than BBR and Cubic. while reducing the average delay by 46% and the tail delay by 44%. Notably, BISCAY's worst case delays are lower than BBR's and Cubic's best delays. This demonstrates that OpenDiag and BISCAY congestion control module are effective together under real world conditions with actual channel dynamics, interference, and mobility. Now, this brings us to the end of this presentation. To conclude, we propose BISCAY, which is a radio KPI based congestion control algorithm. OpenDiag is implemented as a loadable kernel module and has been validated on multiple COTS devices and external models. It has been deployed commercially actually for over a year now. It works without root access, and we package BISCAY as a custom Android image that users flash through the standard mechanism like fast boot mode. BISCAY outperforms all existing state-of-the-art alternatives. Please do check our paper for full set of details result. And please reach out to us in case you have any questions. Thank you so much for listening.